Hello everybody and welcome back to ISOMath. Today we're going to be talking about implicit functions and how to find their derivatives. Here's a couple examples of how we go about doing that. Okay, now earlier we were talking finding derivatives of regular functions. Now we're going to find derivatives of what we call implicit functions. So earlier we said we had equations that were of the form where it's solved for a variable of y equals f of x or any combination of any other variable where y is said to be an explicit function of x. Again, these variables can be interchangeable. You could have t, you could have z, you could have s, but essentially we're solving things that were solved for one of the y values, such as y equals x squared, or likewise f of x equals x squared. Now we run into equations that have the form of this, was essentially we have two variables that are related, and we call that in this case where y is an implicit function of x, meaning essentially they are not dependent on one another, they vary independently of each other. So since there are x values that correspond to two y values, y is not a function of x, around the whole circle, because we know this is an equation of a circle. So that's the kind of stuff we're dealing with. So if we take this example right here, we're going to deal with that one first. And it could also be the form, obviously, f of x equals x squared, and we're trying to find f prime. And here we knew this, using the power rule, we knew that to be 2x. But what we really didn't tell you is that was simply, because what we were asked, if we really break it down even tighter, we're trying to find the derivative with respect to x of x squared is what we're trying to find. And we knew that using power rule was 2x, but really what it really is 2x, and there was an invisible derivative of x with respect to x. You can almost essentially write that dx dx, which we know that to be, obviously just comes out to being 2x times 1. Now it's not really noted there, but if you imagine that we're taking the derivative here of x with respect to x, we can find out that kind of equates. It's useful to use that concept when we're trying to find these guys, because here obviously this guy is going to be nothing more than 2x, and that's the derivative of x with respect to x. I'll put it in this one time, dx dx. And here I'm trying to find the derivative of y squared. Well, the derivative of y squared is 2y, but that is the derivative of y with respect to x. And then obviously here, derivative of a constant with respect to x ends up being 0. Derivative of x with respect to x, but essentially these dx's, they essentially turn into being 1, so this ends up being 2x plus a 2y, but we got to hold this dy dx and equals 0. And what we're trying to find out ultimately here is you're trying to find the dy dx. So what you're going to do is you're going to isolate this dy dx. So going down a little further here, what we're going to end up with that is simply, I want to isolate that term, so I'm going to subtract 2x from both sides. So I'm left with 2y dy dx equals a negative 2x, and then I'm going to divide through by 2y to end up with my final dy dx equals a negative 2x over 2y, or simply a negative x over y after simplification. But essentially what you're going to be solving for all these terms, you're going to be trying to find dy dx is what we're looking for. In that last case, is dy dx equals negative x over y. And that is an implicit differentiation. That's what we're trying to find the derivative implicitly. You're going to be solving for that dy dx. Now in this next example, we're asked to find dy dx of x squared minus x times y plus y cubed equals x times y squared. And again, this is implicit because both terms are not solved explicitly for one another. So we have implicit differentiation. Let's take care of the easy one first. We have right here x squared. That comes out to being knowing. We know that just using power rule being x squared. Over here, we're going to take a break from this guy. We'll come back to him. Then I need to find the derivative of y cubed. Well, y cubed, the derivative using the power rule, is 3y squared. But again, it's dy dx because that guy is the derivative of y with respect to x. And then I have this x and y squared over here, which I haven't found yet. Actually, I'll leave that blank because we haven't found it yet. So what I'm going to do here is just first look at this piece right here, this x times y. Well, x times y, remember, they essentially are, because they're solved this implicitly, they are two different functions. And this becomes a function times another function, x times y. So we have to use the product rule to solve this piece, with the f part being the x and my g component being y. And when I find f prime using my product rule, that's going to be simply 1 dx dx, or 1. But my g prime is going to be 1 dy dx. And yes, I can, like I said, I can carry the dx dx, but we know that's just going to be 1, so I don't have to worry about that. But I do have to worry about that dy dx. And remember, from the product rule, I'm going to have f prime plus g times, or plus f times g prime to put it all together. So this is end up, my piece putting that all together is going to be 1 times my y plus my f, which is x, times the g prime, which is a dy dx. So the component that goes up in here is going to be y plus x dy dx. Now notice these parentheses. It's very important to keep these parentheses, because this negative sign here has to get distributed through both quantities in there. A common mistake when using the product rule with embedded in implicit differentiation. So then over here I got the same idea. I got another product rule. The only difference is this time my f is going to be x again, but my g is going to be y squared. F prime once again is 1 dx dx, or 1. And my y squared, my g prime in this case, is going to be 2y dy dx. Whenever you find the derivative of y, you got to have that dy dx attached to it. And putting it together using the product rule, I'm going to have 1 times my y squared plus my x times my 2y dy dx. And so when they get together, when I put them all together using my product rule, I'm going to have my y squared plus, put the leading coefficient out front, 2xy dy dx. So I found these pieces, but I still haven't completely solved for my what is asked, because it's asked to find dy dx. So to do that, what I need to do in this case is I need to get all my dy dx's on one side and everything else on the other side. So I'm going to do that using like this. So I have 2x minus y, distributing that side, minus x dy dx, plus a 3y squared dy dx equals a y squared plus a 2xy dx, xy dy dx. So I'm going to move all my dy dx's to the left side and everything else to the right side. So I'm going to subtract my 2x, I'm going to add a y to get those guys on the other side. So I'm left with the negative x dy dx plus the 3y squared dy dx. And I'm going to move this piece over, this guy over on this other side. So I'm going to subtract that piece. So it's going to be a minus of 2xy dy dx. And then everything else on the other side is my y squared minus the 2x plus the y. So right now I've isolated, I've got all my dy and dx's on one side and everything else on the other side. So what I'm going to do now is I'm going to factor out this dy dx. So factor out the dy dx. I'm left with a negative x plus the 3y squared minus the 2xy equals y squared minus 2x plus y. Now remember what you're trying to solve for. You're trying to solve for this dy dx, so that means you want to isolate that term. So to do that, I need to divide everything else by this term right here. So my final answer, by dividing everything else by that negative x, all that term over there, I'm left with y squared minus 2x plus y on the right, all over, divided by negative x plus 3y squared minus 2xy. And that is your answer when you're solving the derivative and implicit differentiation of that term. Hope that helps, and remember, check back to ISOmath for all your math needs, and we'll see you soon.